From North Carolina State.
Oh, no, already. So, yeah, Dr. John Blondin is an undergraduate professor of physics at North Carolina State University and the head of the Department of Physics. I got that right. Yeah, very good. Okay, in his most recent studies, and I'm just going off by your website and all the pubs.
Let's hope it's up to date.
I was just trying to sum this up. Make notes. Yeah. I mean, very, very accomplished guy, so I got to make it interesting somehow. His most recent studies are core collapse supernovae and simulation of core collapse supernovae, which utilizes NASA's Xray telescope. And so today we'll be talking about X-ray binary star systems. With that, Dr. Blondin, please take it away.
All right, thank you. The last time I talked to this group, it was down in the basement in the other building. I'm glad to be back. So those of you who don't know me, I've been a professor at NC State for 22 years now. I grew up in Wisconsin, and when I was in grade school, I remember my dad bought me a little set of 4-inch mirror and blank and tried to get me to grind my own telescope mirror. That lasted for about a year, and I just gave up. But then I got the bug again in high school, and this time I was a little smarter about it. I just saved up my money and bought a 6-inch reflector. But being an amateur astronomer in Wisconsin is a challenge. So it means you spend some really, really cold nights or early mornings outside in the dark. In fact, when people ask me how did I get into astronomy, I usually tend to go back to when I was kind of early high school. I had a paper route, and so I had to get that done before school, which meant out at 5 o'clock in the morning, and in the dead of January, the sky was just perfectly black, and I'd be doing the paper route and just look at that amazing night sky, and that really intrigued me. Then, as I was going through college, my next door neighbor was a very famous professor of astronomy. In fact, he was kind of one of the grandfathers of the orbiting telescopes, Art Code. And so he kept trying to push me to go into astronomy, and I kind of liked it, and I was good at physics, so I thought, well, I don't have any better idea. But then when I got accepted into graduate school where he had gone, he was all excited, and so he came over next door and gave me a box, and I opened it up, and it was a 1960s era flight suit with all the heating coils. He said, you're going to need this standing in the observatory on the top of the mountain all night long. And so I think it was then that I decided to go into theoretical astronomy rather than standing in the telescope dome all night long. All right, so this talk is pretty much a talk I gave at Goddard Space Flight Center a few months ago. So please stop and ask questions, because it's not quite tailored the way I should, but it's got lots of pictures in it, so hopefully, and if there's anything you're not understanding or don't understand the pictures, please shout out now that he turned off the lights and I can't see you. No, that's fine. All right, so the work that I do is primarily computer modeling of things we see out in space. And so the topic here is interacting binary stars, particularly X-ray binary stars. So stars, what that really means is that one of the two stars is going to be a neutron star or a black hole. And I'll get into that in a few minutes. So here's kind of a simple picture. See if I can get the laser. No, that's not the laser pointer. Oh, that's the laser pointer. All right, so here what we're simulating here, so this is a computer model run on a supercomputer out of Oak Ridge National Labs. Not mine. So this is a typical high mass X-ray binary system. I'll describe a little bit later, but here's a very normal star, an O star, And orbiting around it, right at the center there of all that mess, is a neutron star. And very simply, the intense gravity of the neutron star is just ripping matter off of this star and forming an accretion disk. But it also forms this big tail of material that swings around. And so while it's kind of an afterthought, that's one of the things we've been trying to study to learn something about these winds is this tail. And in fact, NASA just announced plans for to develop some new small explorer spacecraft, and one of them will be the first X-ray telescope to be able to measure polarized X-ray light. And one of the key sources out in the sky that will produce strong polarization will be this wake. All right, so X-rays. So we're all familiar with X-rays, right? Presumably you or someone close to you has had a medical X-ray. X-rays are very useful because they can penetrate through matter fairly well, but not completely, right? So when a doctor takes an X-ray of your hand, the X-rays are going through the flesh, but they don't go through the bone, so what you get on the image is a shadow of your bone structure. It turns out that our atmosphere has enough matter in it between us and 10 kilometers up that there's enough air there to actually stop the X-rays from space. So to actually observe the universe in X-rays, you have to get your telescope up above the atmosphere. And Chandra is kind of really the big workhorse for X-ray astronomy right now. And so here we've got an optical image of the Whirlpool galaxy, and then the X-ray image. So you can see it looks pretty much the same. But all of these point sources of X-rays are X-ray binaries. So they're black holes or neutron stars in a binary system, somehow sucking matter off of that other star. And as the matter falls onto the neutron star, into the black hole, it's heated up to millions of degrees, hot enough to produce X-ray radiation. So the history of X-ray astronomy goes back to the early 60s. So if you want to see X-rays from outer space, you've got to get above the atmosphere, and that means a rocket. So we had all these German rocket engineers who were shuttled over after World War II and working exclusively for the Air Force. But around early 1960, they started to relax the restrictions a little bit and let some scientists play with these rockets. And X-rays are essentially just high energy radiation. And the simplest way to detect them is with just a generic Geiger counter. So basically what these guys did was stick a Geiger counter on top of a rocket and launch it up, and it would go above the atmosphere. It would kind of hang there for about 5 minutes. So you only get a few minutes of observation, fall back down, you read the data, and one of the, so they first saw the sun, but then SCO-X1 was the first cosmic source discovered, and you can see it took about 5 years for them to come up with this idea that these X-rays are produced by gas falling onto a neutron star that's in a binary system. In fact, that was pretty remarkable because not many people believed neutron stars existed at the time. So I'm always amazed that they got this picture right in this article. But then the truth is, if you go back to 1967, that journal, and start reading some of the other papers, most of them are just crazy. They're just way off the mark. This happened to be the one that they got right. All right, so there's lots of artistic renditions of X-ray binaries. You just Google X-ray binaries and get all sorts of cool pictures. They all have matter flowing from one star, spiraling into an accretion disk of some sort. I don't know what this artist was doing. And this one just got it totally wrong. So here's our first attempt to actually model the physics of the disk itself. We didn't actually model the transfer of mass from the star. But this is from the first three-dimensional simulation of an accretion disk around a compact object. This was done by Mike Owen, who got his PhD back in the late 90s. I'm going to talk about, we classify these X-ray binaries into two different classes, low mass and high mass. That's basically the star that's giving up the matter. Is a small star smaller than the sun, or is a high mass star that's much bigger than the sun? And so I'm going to skip a lot of these details. All right, so the basic idea of what I'm trying to do in this research is to take some observational data. So here's an example. Vela X1, which we do a lot of times, we spend a lot of time studying this object that's very well observed. We've been studying it for 40 years. But those dots are showing a plot of the pulse period over a time scale of many weeks and months. And what we're seeing, the pulse period, these X-rays are pulsed because of the lighthouse effect. The neutron star that's producing this X-rays is spinning, and it's just emitting a beam of X-rays. So every time that lighthouse of X-rays faces you, you get a pulse, and then the star continues to turn, and then you get another pulse. So that pulse period is telling us how fast the neutron star is turning. Okay? And those periods of order seconds, which is kind of mind-boggling if you think the neutron star is the mass of the sun squeezed down to fit inside Research Triangle Park. All right, so you imagine, right, how long does it take you to go to Durham and back? Right. Here we've got a star the size of the triangle spinning all the way around once in only a few seconds. So this thing is spinning really, really fast, which in itself is amazing, but the fact that it's changing tells us something is trying to spin it up, so the pulse period gets smaller, and then slow it down. So there's something really funny going on there, trying to slow it down, spin it up, slow it down, spin it up. And so that's the kind of observational puzzle that we go after to try to understand what's causing that strange behavior. Yes? Yeah.
Bipolar axis.
Yes.
Spinning around. So there could be neutron stars that we actually can't see a pulse from.
Absolutely, because it's not pointing at us. Yep. Yeah. So in fact, so these neutron stars are highly magnetized, and so the process is very much like the northern lights. All right, we've got the solar particles coming into Earth. They get funneled to the magnetic pole by the magnetic field of the Earth. And that's where those cosmic rays, or solar particles, are interacting with molecules in the atmosphere and start to make it glow. So same idea, all the matter falling onto the neutron star is funneled towards the magnetic pole, and that's where they release all the X-rays when they crash onto the surface of the neutron star, and most of those X-rays are just shooting out in a beam of X-rays rather than everywhere.
So they're generated by impact.
Yes, by the impact onto the star in the case of a neutron star. In the case of a black hole, it's more complicated. The X-rays are coming from the inner edge of the accretion disk just as it's about to, the matter's about to fall into the black hole.
Some of those brilliant color images you would show in there, I would assume that's probably just someone's artwork.
That's exactly right. It's all false color imaging. Yeah, and I don't know if you saw, there's been some news stories with Stephen Hawking about his black hole stuff in a conference, and so they had some pretty cool pictures there. All right, so what I'm doing is taking the physics equations that describe how matter moves about and try to apply them to how does matter get from one star to the other and ultimately fall onto the neutron star. And so this is just this is an animation that we created back in 1991. So this goes way back, but this is basically exactly what we've been doing, only now we can do it in a much bigger model in 3 dimensions, and I'll show you where we go. So the idea here is the matter that's falling onto that neutron star right at that point, at sometimes you can see it spinning around one way, at sometimes you can see it spinning around the other way. And so this kind of chaotic behavior of this flow trying to get from one star to the neutron star naturally explains why sometimes you're trying to make it spin faster and sometimes you're trying to make it spin slower. All right, so I threw this in because it was up at Goddard when I gave this talk, and so this was the first simulation of X-ray binary, which I did when I was at Goddard in 1989, so ancient history. Thank you, Microsoft. At least they're sorry about it. All right, so PowerPoint. Okay. All right, so I wanted to put in a quick plug here. So a lot of the work I'm going to show is actually done by students at NC State. And this is a summer research program that we've run for the past 3 years, and we just submitted a proposal to the National Science Foundation to run it for another 3 years. So 8 students come in, and they learn how to do this kind of research and do their own project. And a lot of what I'll be showing you are the projects that they completed. So we would go to, there was a similar program over at Chapel Hill. So ours was undergraduate research in computational astrophysics, and theirs was computational astronomy and physics. So in the middle of the summer, we'd go over there, and the students would show posters about everybody's work and kind of mingle. And then we'd go to a theme park somewhere in the triangle between Chapel Hill and here. I don't remember the name of it, but we play the Chapel Hill students in laser tag, and so we beat them 3 out of 3 times. All right, so let me, all right. So there's basically 2 ways that this neutron star black hole can get mass. So somehow mass has to fall onto this compact star to produce the X-rays. There's kind of 2 ways. One is it has enough gravity that it literally just rips matter off the star. And I'll do that one later. This one is where the gravity isn't quite so strong, but it's strong enough that if the companion star over here is producing a wind, right? Our sun is producing a wind and it's flying past the Earth. So all stars have some kind of wind, but these massive stars have very dense wind, lots of matter falling off. And so the matter blowing out in the wind, if some small fraction of that wind can be pulled in by the gravity of the compact object, then it can be accreted and produce the X-rays. So we call this wind accretion, and it was first proposed in the early 70s. But using some interesting theory that goes back to 1939. And I'm amazed by this. So you go back and read it, and what these guys, Hoyle and Littleton, so this is Sir Fred Hoyle, is they're trying to explain climate variation. Thank you. So what happened back in the mid-30s, that was just when they were discovering that space is not empty. Right? Up until this point, they assumed, once you got out past this atmosphere, it was just empty. So they were discovering that there's gas and dust between us and neighboring stars. And so what Sir Fred Hoyle pictured was, all right, we know there's these clouds of gas and dust. Well, if the sun wanders through one of them, and because of its gravity pulls some of that gas and dust onto it, that extra material falling onto the sun is going to make the sun brighter, and that's going to explain global warming. So it turns out that that's not the case, but it's only not the case because the sun has this wind that's kind of creating this protective shell around it. So I don't know if you remember a few years ago, some of the early Voyager spacecraft finally got out of this protective shell and out into true interstellar space. But if it weren't for that solar wind, this would actually be a reasonable theory for climate variation. So it doesn't explain planets, but it does explain these X-ray binary stars. The interesting thing is that these guys they proposed this theory in 1939, and we didn't have the computer power to actually model it until 2012. So there's just a long history of people trying to attempt it. The picture, keep hitting the wrong button. The picture's here. So you picture the wind coming from this side. So there's wind, interstellar wind coming this way. And so you have 3 different time shots of this accreting neutron star. And so basically there's a wake behind it, but that wake wobbles back and forth. And so that was discovered back in the mid-'80s by a group of Japanese and by Bruce Fricks and Ron Tom at Northwestern. And so a lot of people studied this, but they were all doing a horrible job of it, only because it requires a lot of computing power to be able to do this right. And so finally, a student here at NC State, Chris Pope, it's not that Chris was any smarter than those guys. He just happened to have access through Oak Ridge National Labs to the biggest computer in the free world. And so he could finally do the problem right. And so in this simulation, the wind is coming in from this side again. So wind coming this way, the neutron stars in the middle there. And what he discovered was that it always managed to turn into some kind of accretion disk, which nobody ever pictured happening. So this was just totally contrary to anything the scientists had predicted up to this point. So this was a junior at NC State coming up with this new theory. So it was pretty cool to watch everybody kind of take notice of Chris's work. So here he made a video, and so you can see all the gas kind of spiraling in. So again, the matter's coming in like this, hitting a shock wave. So this is about a Mach 10 shock wave. And then behind the shock wave is where it falls in towards the neutron star and tends to fall in a spiral pattern. And so all the X-rays would come in from that inner region, right, where it's spiraling into the neutron star or black hole.
What is the scale?
Good question. The scale for typical parameters would be thousands of kilometers from top to bottom.
How about time? Is that like days?
No, good question. This time turns out to be about 20 seconds times that time. So we're talking about minutes, which is part of the problem because we can't compute for we can't simulate for more than an hour yet. You want to explain how these things behave over days and weeks and months. So we're still limited. But the key here is that the matter falling in is rotating really, really fast. And that was the piece that was totally counterintuitive to everything people had thought beforehand. All right, this movie goes forever, so I'm going to jump.
It's like rolling.
Yes, and in fact, what happens late if we sat and watched this for a long time is that actually the bow shock collapses and the whole thing reforms, rotating in the opposite direction, which is an explanation for that Vela X1, which for a long time was spinning up and then it was spinning down. And so here we have an example of how that might happen in nature. But yes, it's the interaction of the spiraling matter in here pushing back on the bow shock. But it's not, I think I know what it is, but it's trying to convince everybody else that I know what it is that is the challenge right now. So what we discovered was in all these models, they all tended to form accretion disks around the neutron star. However, these are all two-dimensional simulations. We're faking it, Okay, we really live in a three-dimensional world. So the question is, what happens in 3 dimensions? And it's really only been in the past 5 years that computers have been big enough that we could run 3-dimensional simulations. So what we're doing is we're using the supercomputers at Oak Ridge and at Texas. The processors in them are just high-end AMD processors that you could put if you had a nice workstation. But there's hundreds of thousands of them. So we're typically running these simulations on about 50,000 processors at a given time that allows us to do 3-dimensional. Yeah.
It's kind of a crazy question here. If we're actually looking on top of a accretion disk,
Right.
but hey, we're also looking directly at the blackboard chest. That implies that there's 2 axes of rotation.
Yes.
Okay, so that's and we turn around. So you see opposite.
Yes. But to do that right, again, we really need to go to 3 dimensions. All right. So yeah, the upshot of this is that 2 dimensions is just a little phony. So what do we see in 3 dimensions? The switching. Yes. I'm doing something Microsoft doesn't like. All right. So what happens in 3 dimensions? So here I was all excited because we had discovered these accretion disks and it was changing the paradigm. And then we go to 3 dimensions and no disks. In fact, these things just turned out to be remarkably steady. So what we're looking at is the flow is coming down from up here, and this is the bow shock. We've cut away a piece of the bow shock so you can see inside, and that's the accreting star. Now in 3D, we have to make the accreting star really big. We just pretend it's much bigger than it really is, otherwise we just couldn't compute it. But the key here is that if you look at the downstream flow, it's perfectly symmetric. It's not breaking into a disk would be in this plane. So you'd see a line rather than a circle. So there's absolutely no evidence of an accretion disk here. So sometimes the science just turns out to be much more boring than you were hoping. All right, so here we go to, this is kind of state-of-the-art observations of this Vela X1 system. But just to point out that these things, the X-rays coming off are very erratic, right? So we're looking at how bright it is. So literally how many photons per second is the observatory measuring versus time. And this is, days spanning 2 months, so November, December. So you get these very, very bright flares. So the X-rays come in these bright flashes. But even when it's not flaring, there's still a lot of variation going on. So this was detected by the Integral satellite. So this is a European satellite looking at X-ray, high-energy X-rays, which the advantage of this satellite is it's not pointing at any one point in space, but it's detecting these high-energy X-rays from everywhere. So it allows it to kind of observe everywhere all the time. And so it's actually discovered dozens and dozens of these new X-ray binary systems because it can see deeper into the galaxy with the higher energy radiation, and it can kind of track everything out in the universe all at the same time. So the last several years, we've kind of got a much different picture of these X-ray binaries. It's having very high variability, lots of very bright flares. And the picture that the astronomers kind of imagine is that this is a neutron star gravitationally catching wind from a companion star. But what they picture is the wind is just filled with lots and lots of clumps. It's not a smooth wind, but it's a cloudy wind. It's lots of clouds being blown out. And if one of those clouds runs over the neutron star, then all of a sudden you get a huge flash of X-rays as all that extra matter falls onto the neutron star. So a very simple theory. And so our students were challenged to verify, does this theory really make sense? So one of these summer students set up a simulation where she would have flow coming in like this and accreted onto the neutron star, which is right at the point there. But then in the flow, you just put a big clump, where it's 100 times denser than all the rest of the gas, and just see how much gas falls onto the neutron star. So that old 1939 theory predicts a target area such that any material that goes to that target would get accreted onto the neutron star. So there's a very simple theory. She set up the experiments, see what would happen. So what you would expect is that when this thing accretes, you get if this is 100 times denser, you get a flare that's 100 times intense X-rays than normal. So very simple prediction. But what she found was when the clump hit, the X-rays actually shut off. What happens is if the clump isn't exactly in the center, the clump kicks everything into that accretion disk like we saw before, and that accretion disk prevents material from reaching the neutron star until the material in the accretion disk gets hot enough and falls onto the neutron star, and only then later do you get a flare. But in fact, the amount of X-rays coming out here turn out to be much smaller than all the deficit of X-rays here. So you end up actually choking off the X-rays rather than enhancing the X-rays.
John, if that actually happened, then it would be periodic, right? It'd be kind of chaotic.
Definitely. Right. So what you'd like is a nice long time series of Veil X1 and see, does it show some kind of quasi-periodicity? Is it totally random? Yeah.
So if that hadn't been a plausible theory, then could you determine the density of these clumps?
Yes.
Based on the.
Yep. So in fact, I think we're reaching that point where we're getting enough observations from the integral satellite, and we're now capable of doing the simulations so we can actually start addressing some of those quantitative questions. So again here, so the next part of the fun of doing these projects over the summer is you learn something one summer, and then the next summer a new student comes in and you can hand them kind of the next step of the project. And so this was done by Eve Chase, who was a student from William and Mary. And so she came in, and her job was just to do this in 3 dimensions. The previous one was 2D, and this one was a movie. All right, so remember, before we went from 2D to 3D, the accretion disk totally disappeared. Here we accrete that clump in 3D, and we still do get the accretion disk. In fact, almost all the clump turns into a disk rather than being accreted onto the neutron star. And that accretion disk sticks around for many hours before it finally blows away. So again, there's all these physicists in Germany and England trying to tell us how these clumps are accreted, and it's a freshman from William and Mary who actually shows how it's really done.
So if it blows away, what's left?
Then it presumably the X-rays go back to a quiet state, or very little X-ray accretion. But the reality is there's probably more clumps coming in. So the follow-on project there, perhaps next summer, is to put in a whole bunch of clumps and see how you hit it, you form a disk, but before that disk goes away, you hit it with another one, and see what do you get.
That looks like a Halloween image.
All right, so here we try to put it all together where we have the donor star. We have a wind coming off the donor star, although you can't see it just because I've left it invisible. But then where the gas gets caught onto the neutron star, which is right there, you form a dense bow shock and this wake going behind it. So this is the first attempt to really try to model this whole thing in 3 dimensions. And so here, the movie actually turns out to be a little boring because the disk really doesn't change shape a whole lot, but this kind of puts it all into perspective. We don't think stars have a hole on the top. That was just a convenient way to run the simulation. But this kind of gives you the proximity of the neutron star to the surface and the time scale for how these things change. So the orbital periods are several hours for these things. They're really fast moving around each other.
If we could see these things, they would be visibly deformed.
This particular one, BLX1, is not, so it turns out the star is not spherical, but it's not super distorted. So it is kind of hard in this case. Some of them are more distorted. So again, this is another student project from last summer. In fact, this video is up on the immersion wall in the Hunt Library. But what he's illustrating here is all the matter that accretes on a neutron star is really just coming from some small patch on the star. So he's launching a bunch of tracer particles, and most of them get caught up in this accretion disk. So you can see the material going around in a circle there. And then some of them end up in this wake that wraps around the star. Okay, so that student discovered that if you let the X-rays, so when more matter falls onto the neutron star, it produces more X-rays, but those X-rays are then going to heat up the wind and change the behavior of the wind and change how much of the wind is caught onto the neutron star. So there's a feedback. You produce more X-rays, you heat the gas, you get less matter coming off. Then the X-rays stop, you get colder gas, more of it can fall in, but that produces more X-rays, so you jump between high X-ray luminosity and low X-ray luminosity. So on a time scale of many hours, he's found a mechanism that actually can produce flares, sort of like you see in VLX1. They don't quite match, but we're looking at other X-ray systems where this might actually be a theory for how you get those flares. When I saw this, I was very excited. The student didn't know what he was looking at and was kind of confused. Why is Dr. Blondin so happy with this? It looks boring. But that may turn out to be a very, very exciting avenue of research, but we're not finished yet. All right, so let me just finish with this other type of mass accretion process. This is more the case for these low mass systems where the neutron star is close enough to the companion that it really does very strongly distort the star to the point where you're essentially just pulling matter off of the star. So this is the inner Lagrange point, or the L1 point. So it pulls matter through the inner Lagrange point, comes in, and forms the accretion disk. And so here's, again, a student project. This is a student, Sam Kenny, who's now a grad student doing condensed matter physics at NC State. But this is work he did when he was a first semester freshman at NC State. And I gave him the data and asked him to analyze it. So this is one of these binary star systems. But what he discovered was that at the L3 and L5 points, there's kind of a tornado effect creating strong vortices, which in hindsight you kind of convince yourself that that should happen, but nobody had really thought about it and predicted it. So this freshman discovered this, and he made a movie of it, and we went up to a national conference in Washington, D.C., and he submitted the movie for their visualization contest. And on the last day of the meeting, up in Washington, D.C., they had a kind of an awards banquet, and they were giving out this award, and they call his name, and he was sitting next to me in the audience, and I could see his fingers just kind of tense on the handrest. He didn't know what to do, but I finally got him to get out of his seat and walk up and collect his award. So he came back all excited and wanted to do more work, and so the system we're trying to model here is HER-X1, and we know that the accretion disk in HER-X1 is not flat with the orbital plane, but it's tilted. And so it seemed like, okay, that should be a fairly simple project. We're just going to rerun the simulation, but we're going to tilt the disk. So I asked Sam to figure out how to do this. So, you know, he's a freshman. He knows a little bit of calculus, but this turned out he just had to teach himself all sorts of linear algebra and an awful lot of mathematics, but he finally he finally figured it out and produced this model. And so what we're doing is we're in the frame of the neutron star and the companion star sitting still, but they're really orbiting around each other. But what we see is that tilt then precesses, and so sometimes the stream of gas from the star is on the top and sometimes on the bottom. And so he continued the simulation and discovered that that tidal stream hitting above and below actually carves out an empty space in the accretion disk. So you really have an inner disk that's very flat and precesses on its own, kind of independent of everything else. And then you have this fat outer disk that precesses on a different time scale. So this was, again, something that the student just a completely new idea discovered. And we go talk to astronomers up at Harvard CFA, the Harvard Center for Astrophysics, and sure enough, they had some observational data that was suggesting that there's an inner accretion disk that behaves completely independent of the outer disk. So this turned out to be a really cool discovery on the part of the student.
Looks like soft serve ice cream.
Yes. So, all right, so that's the conclusion. So the main idea is that we're able to use these big 3D computer models to really understand what we're looking at in space. But at a minimum, we can at least add a little bit of physics to all these cartoon models that we draw about all the stuff we see in space. But hopefully we're learning something through this process, as well as teaching students how fun astronomy is. Thank you.
Okay, question and answers, or we hope you got answers.
Yeah.
So how does these accretion disks compare to like a shell star? Because I would think shell stars you can see in visible light, easier to observe.
Yes. So in those stars, the gas is moving gently outwards, but it's still a disk. So here, because the intense gravity of the central source, this stuff is spiraling around at very, very high speeds. Whereas in shell star, B star, and those kinds of things, it's a much gentler rotation because it's on a larger scale, less gravity. As far as how you can observe them, you know, the best thing is you observe them in radio infrared as much as you can get, because the more photons and the more information you get, the better you can understand them.
With the accretion of this gas at such high speed under extreme gravity, is the gas dense enough to get into the effects of high-speed interfering jets, like they had some in that shuttle that disintegrated, which they didn't really expect. But that's very low energy stuff. Or is it really very?
It's possible. We're totally ignoring those effects. So all this stuff is not really a gas like the air in this room, but it's an ionized plasma. And so that means that all the molecules or all the atoms are ionized. You've ripped all the electrons off, and now these electrons and the positive ions are spinning around the magnetic fields. And so if you look on the small scale, you see all these strange effects, jetting and different kinds of waves. On the big scale of the star, it's still behaving like a fluid. So we're just doing the big scale and ignoring that kind of physics.
Got to do it step by step.
Yes, we'd love to be able to do it, but it turns out putting the magnetic fields into the simulation is really hard, and that's a field of physics that's just kind of struggling. Yeah.
So with, I know this might be a stupid question, but is there what kind of electrical field?
Not much because this is a plasma. Okay. So the electrons and the positive ions will quickly neutralize the electric field. Yes. Yep. Except once you get down to the surface of the accreting star, and there you can get enough of a charge separation that you can get strong fields. Yeah.
So just within a neutron star, all the electrons, protons have been squeezed out, and all we have are neutrons.
In the star, yes. Yep.
As this matter hits the neutron star, basically all that stuff's being stripped away. Is that correct? And so it's being basically assimilated on the star.
It's being assimilated on the star, and so what you end up with is kind of on top of this neutron star, you've got most of the gas coming over from the other star is hydrogen, right? Because most stars are made of hydrogen and helium. So what you end up with is an ocean of hydrogen on the surface, right? But it's extremely dense and hot, and if you get enough of it on there, you'll trigger a thermonuclear runaway, and all that hydrogen burns all the way up, burns to carbon, oxygen, all the way up to iron, and so you get a thermonuclear flash of X-rays. And so there's a whole other set of systems called X-ray bursters that are presumably driven by these thermonuclear flashes of what's being assimilated.
Is this a never-ending process? Does it ever end?
What most likely, particularly in the high mass X-ray binaries, the thing that's going to end it is that O star is going to die, right? It's going to run out of fuel in its core, and it's going to explode in a supernova explosion. The end result then would be, if that supernova explosion leaves a neutron star, then you'll have a binary neutron star. And we've got 5 or 6 examples out where we see out in space 2 neutron stars orbiting very close together. In fact, the Hulse-Taylor pulsar, right, Joe Taylor won the Nobel Prize for that, studying that system, because it shows direct evidence of angular momentum loss due to general relativity. So while we've never actually detected gravity waves, that really is the only way to explain that binary neutron pulsar